we go. So you got your formula sheet out, you got your calculators because you're going to follow along that way. That's going to be your precipitation. I guarantee you, if it's going to be forces, angles, ramps or Atwood machines at angles or stuff like that, because that was physics 12. Everything else was really physics 11. What were the key ideas behind forces? Good free body diagram, and then we used our winner minus loser approach. Oh, but if we were on a ramp at angles, we broke everything up into components. So this says a 2.4 kilogram block is sliding down a 32-degree incline with an acceleration of 1.9 meters per second squared as shown. The coefficient of friction between the block and the incline is 0.13. What's the applied force FA acting parallel up the incline? Okay, let's find out. What are the forces acting on this block? Get the obvious one. Okay, so we're going to start out by saying, all right, I'm going to label gravity. Got to start out by actually giving me my pens back. So we would say this. We would go mg straight down. And we would break this up into perpendicular and parallel. We called it mg parallel, and we called it mg perpendicular. And we said that this angle being 32, Nico meant that this angle here was 32 degrees. We did a proof, and then we just kind of memorized that. You can walk through the proof if you need to. What else? Which way? Not straight up, always perpendicular to the surface. And you know what? I can tell you it's going to be just as long as that mg perpendicular. In fact, you know what? Since it's not a component, I'll do it in blue. It's going to be just as long as that mg perpendicular component that you see. What else? Which way? Because the block is moving down, I'm going to have friction up the ramp. And what else? I'll just circle that guy to make sure I don't forget him since they already put him on there. I don't like a free body diagram where the arrow ends on the mass, but I'll live with it for now, Sebastian. I've circled it, it'll stand out. We said from here, we're going to go to a winner minus loser approach. We're going to say, who's winning? Which way is the block accelerating? Down the hill. Who's winning? Okay, so my equation's going to look like this. mg parallel, and any other forces down the hill are going to be winning. Are there any others? I don't see any. Who's losing? Who else? What does that equal? My net force, and my net force was just ma. All right. mg parallel, let's see. This was hypotenuse. This was opposite. We know the hypotenuse. I think mg parallel ended up being sine. In fact, I think it was someone here who said specifically for these diagrams, 2 lines is sine. Well, you can use that, or you can rederive it. So if I moved it, whoop, a little too far, Mr. Dueck. Keep it still on here. If I try writing my equation, it's going to look like this. mg sine 32 minus, that's what they're asking me to find. I'll get that by itself in a second. Minus friction is what times what from your formula sheet? Mu times the normal force. I've never, ever, 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 ever said mu mg, and I never will. It's mu times the normal force. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force, and don't you dare say mg, because it's not. Okay, it's going to be mu mg perpendicular. That equals ma. By the way, in this question, do the masses cancel? No, they did sometimes. In fact, if I didn't have that applied force here, yay, the masses would cancel. I'd probably give you the mass in the question, although I might not. You might be freaking out. Oh, no, masses cancel. This time they don't. Mg perpendicular, which trig function is that going to be? Okay, so this is going to become mg sine 32 minus fa minus mu mg cos 32 equals ma. You gonna make it? Yeah. Okay. So far, so good. This would be easier if I could somehow keep all this. You know what? Let's go like this. Work side by side. Let's get the FA by itself. I think I could plus the FA over to the right-hand side, yes, and minus MA to the left-hand side at the same time. I think we'll end up with this. The applied force is going to be mg sine 32 minus mu mg cos 32 minus ma. All right, let's start plugging in numbers. What's the mass according to this question? 2.4 times 9.8. This is what you're going to follow along on your calculator. Minus what's the coefficient of friction? 0.13. 2.4, 9.8 cos 32 minus 2.4 times what they say the acceleration was, 1.9. What do you get? $5.3? Anyone else? I need a consensus. I need a better consensus. 5.3, 5.3, okay. Units? It's a force. Newtons. Okay. That's a quick review of almost everything we can throw in terms of forces and angles. Now, how else could I change this? You know what? They gave you the acceleration. What if I gave you the distance and the time and the initial or the final speed? You could calculate the acceleration using unit 1 stuff. F equals VI, AT, D equals or VF squared. That would be totally fair game. Or I could have given you the applied force, and I could say find something else. For example, I could say find mu, the coefficient of friction. In fact, that's really about the only something else I could ask you to find. I wouldn't ask you to find theta. That would be fair game next year in university, but not this year. And I wouldn't ask you to find the mass, because that's kind of boring. Okay? Forces at angles. We also did Atwood machines at angles as well. I'm not going to do one today, but look at those too. An Atwood machine at angle was where you had one hanging over the cliff and the other one going down the ramp at an angle. If you look at your quizzes, you'll see we did a couple like that in the actual quizzes. I think the last forces quiz, we did one like that. Going back. Oh, so here's an example. A block accelerating down a 34-degree slope, find the coefficient of friction. So there's something else I could ask you for. Although if this was a written question, I would make you calculate the acceleration. I wouldn't give it to you. I'd give you enough data that you could find it. Okay? Momentum. So one of the things we looked at in momentum was collisions at angles. That was new to Physics 12. Got to remember where I'm going here. Question? Or comment? Talking to Joe? Yeah, shut up. Okay. So here is one I found. This looks fairly tough, actually. I yoinked this from an old, I yoinked this from a recent provincial exam. What do you see? Is there a collision? This is a job for momentum. So we always started out, by the way, what if there was a change in height? That was a job for conservation of energy. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. So a change in height, we used work and energy. Collision, we used momentum. We started out the same way, whether we were in a nice straight line or not. We started out by going the sum of all the initial momentum before the collision equals the sum of all the final momentum. Then we asked straight line or angles. Look at this question, straight line or angles. If it was in a nice straight line, we usually just let to the right be positive and to the left be negative. Okay. Here, we're going to dulp. Going to draw a picture. Going to make it, Zach? Before the collision. Momentum 1 initial. And I can even tell you what it is. It's going to be mass times velocity, which is what? Which is what? You're following along. 1.5 times 72. 108 exactly? Okay. I have 108 magnitude and due east, if you want to call it that way. Wham! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Separate. Angles or nice straight lines? I better dulp. So I'm going to have that. And that looks like the smaller mass, looking at my diagram. This looks like momentum 1 final. And they did give me the velocity, and I know the mass. Can you find the magnitude of this arrow? Can you go 1.5 times 43, please? 64.5? Plus momentum 2 final, I don't know. Okay? Oh, and there is a 55-degree angle here. What side do I have two momentums on? Okay, I'm going to add those two together. How am I going to add those two together? Draw them. I'm going to draw them tip to tail. I'm not quite sure how this is all going to work. Let's see. This looks kind of yucky to me. And they want me to find that theta there. And I know that when I add them together, they need to form a nice straight line. I may have picked a really nasty momentum question. Let's see. It's going to look like this. 64.5, yes? Plus, when am I going to stop? Right there. Why? Because I know the resultant. The resultant is supposed to be a nice straight line, and I know the resultant is 108. I know this angle is what? 55, so I need that angle. 135. This isn't as bad as I thought. I was a little worried. 125, yes. What am I listening to Brett for? Never again. I don't like the fact that I drew my triangle this small, but whatever. And I think my scale is all to garbage, but whatever. Although I'm pretty sure I'm expecting momentum 2 to be fairly big. Looking at it, it kind of looks like a hypotenuse, but it's not a right angle triangle. Oh, this is a job for the cosine law. What's the cosine law? Here's momentum 2 final. The cosine law says this. Momentum 2 final squared equals 64.5 squared plus 108 squared minus 2, 64.5, 108 cos, what angle, Brett? 125. Calculator and square root, please. Remember, cosine law is right on your formula sheet. Tell me the magnitude, please, of momentum 2 final. Which is why I dropped the vector symbol. Calculator, following along. This is your participation. Because I'm not making you write this down because I don't have this photocopied. You'll participate by, and clue in, typing in the numbers reinforces the action. You haven't figured that out already. What'd you get, Sebastian? 154. Sorry? 154. Give it to me to like 5 sig figs because I'm going to use this to find my actual answer. 154.32. Is that correct, folks? Anybody else? Yep. Which kind of meshes with what I thought. I figured it'd be even bigger than the 108 because it looks like a hypotenuse in my diagram, so I'm good with that. That's the momentum. That's not what they asked me to find. They asked me to find the velocity. If I know the momentum, how can I find the velocity? Okay, so the speed of object 2 is going to be the momentum of object 2 divided by mass 2. It's going to be the number you have still on your calculator, woohoo, divided by, now mass 2 was from the top there, can you read how big? Or from the picture? 8.3. What's the speed? Louder? 18.6 meters per second. Now that's the speed. They wanted the velocity. I need an at. What at am I going to find? I think the best at to find would be this angle right here. Because if I find that angle, even though it's not in my triangle, that's going to be what of what? South of north, east of west, what of what? Going to be south of east. So if I find that angle, it's going to be south of east. Problem, that angle is not in my triangle. Or is it? Oh, I got a Z. Sebastian says, hey, Mr. Dueck, you have alternate interior, come on, alternate interior angles. You have them right there, which means that this angle is going to be the same as my angle up there. I can do this, Mr. Dueck. So, I'll put my theta right here. How will I find it? Sine law. I'm going to do it right here because I got room and I'm trying to cram space in. It's going to be the sine of the angle that we know. What's the angle that we know? Divided by the side across from it, which we now know. It's momentum 2 final. This is why I said carry a few extra sig figs, by the way, as well. 154.32 equals the sine of the mystery angle that we don't know divided by the side across from it, which I know, 64.5. We're going to cross multiply successfully and accurately, I trust. I think you're going to get this. the sine of theta is going to be 64.5 times the sine of 125, Mr. Dueck. 125 divided by 154.32. On your calculators, can you go 64.5 times sine 125 divided by 154.32? And that'll give you the decimal value, hit equals, that'll give you the decimal value of the sine. How do I find the angle that it came from? Okay, inverse sine of that. What'd you get, Nathaniel?
20.02 after the inverse.
20.02, so 20 degrees even? Pretty close? That's a nice answer. South of east. Okay. Good chance you'll see one of those, because that was physics 12. Basic conservation momentum was physics 11. The other thing you'll see that's possibly physics 12 is a combined energy momentum question. Now, if I do that, it won't be at angles. That was, for example, where we had a roller coaster coming down a hill, colliding with a stationary coaster, and then how far up the next hill do they move? You had a change in height. That was a job for conservation of energy. Wham! They collide. Then you had a collision. That was a job for momentum to find the new velocity they were going to move off together, and then a change in height. You wanted to find how high up the next hill they moved. Okay? Trying to remember, do I have one of those? Oh, sure, here. Got 9:06. Yeah, I got time. Okay. No, it's not a Word document, Mr. Dueck. Think about where you're cutting and pasting. Back to here. Paste. Okay. A 3-kilogram car traveling 8.5 meters per second on a frictionless track collides and sticks to a stationary car. The combined cars will reach what height, h? Is there a collision? That's a job for momentum. Is there a change in height? That's a job for energy. Collision. The sum of the initial momentum equals the sum of all the final momentum. Vector is important, vector is important. But are we in a straight line or are we at angles? So you know what? I don't think I'm going to dulp. Could, but I don't think I'm going to dulp. Before the collision, what's moving? Mass A, mass B, or both? So it's going to be mass A, velocity initial A. Wham, they collide. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? So it's going to be mass A plus mass B times V final. You want V final? Could you find it? How would you get the V final by itself? Okay, we're not even going to walk through there. Then over here you would say kinetic is change in height, potential initial equals kinetic energy final plus potential energy final. Okay. Oh, how could I maybe change this? Maybe I could give you the height and then say how much did we lose to heat? You'd still have to find the initial velocity to see how much kinetic energy you had to begin with. That would be a nice little addition. Or I could give you a collision question and say how much energy was lost to heat. I could give you a straight line collision and have something bounce backwards. Now, if I have something bounce backwards, what am I going to call that velocity if it bounces backwards? Negative. I'll have to, right, if it's straight line, I do have to be consistent in my frame of reference. Let to the right be positive, to the left be negative, or let to the left be positive and to the right be negative, whatever you feel, just be consistent. That would be nice ways to do it as well. I could then, and then ask you for, hey, what's the change in kinetic, or how much energy did we lose in the collision? Find out how much energy there was before the collision, find out how much energy there was after the collision. If you haven't clued in, what I'm saying is you're probably going to get some kind of a question that combines energy and momentum in one question, like this or some kind of other tweak. Is that okay? You guys are okay solving for H final? We've done that a bunch, I hope. Then we moved on to circular motion and gravitation. So here's one. The planet Gleam, nice name. A 1.5 kilogram rock above the surface of planet Gleam drops off a ledge and falls 20 meters in 4.1 seconds. The radius of the planet is that. Determine the mass. Say what? Say what? Talk to me. Show. Show said FG equals FC. Are we in orbit? Are we in orbit?
No.
Shut up. Okay. No, I'm glad you did that because that was a reflex. That was one of our most common questions. This is a little mini curveball. We're not in orbit. So, by the way, if we are in orbit and it's not talking energy, absolutely that's the first thing you'll write. And I'll tell you, one of your questions probably going to be something to do with orbits because I'm nuts about that. We had a Canadian on the space station this year. So, yeah. How about here? Pardon me? Try to find M2. How? Dylan, what did you say? Ah! Are we on the surface of this planet? Then I think we can say this. This may sound very obvious. I think we can say gravity equals gravity. However, we have two ways to do gravity. Cosmic and on the surface. Are we on the surface? So on the surface, we always just did this. Now, this is not G 9.8. This is G of this planet. Yes? And what was the cosmic Newton's universal gravitation? Big G, big M, little m, over. Okay, now what? Hey, cool. I guess big M is what they want us to find. Let's get that by itself, shall we? How? Times by r squared and then... Okay, so the mass of the planet is apparently going to be little g r squared divided by 6.67 times... Do I know the radius of the planet? Do I know big G? It's on 6.67. It's universal. Do I know little g? Not yet. What is little g? We gave it a name. We called it something. Ah, Dylan's been doing his homework. It's louder, Dylan, my friend, who I like now more than any other student in this class. We called it the gravitational field strength. What's the gravitational field strength here on the Earth's surface? Really? Huh? How could you calculate the gravitational field strength here? Where else did that 9.8 appear here on the Earth's surface? What else was it that we used in Physics 11 all the time? Acceleration due to what? Did they give me enough information in this question to find the acceleration due to gravity on this planet? Well, what haven't I used yet? Ah, we can find... What else do I know? Yes? What else do I know? It's a vertical displacement, yes? It's not 20. Why negative 20? You ending up below where you started from? What else do I know? If we drop something, you know something. If you had me for physics last year, I drummed this in. Huh? Do I have an equation that has d, t, v initial, and g, which is an acceleration in it? What? Ah, this is good. This is Physics 11. Good gosh. At least it should be. I put a G in for the A because that's what we're talking about here, because you said it was the acceleration due to gravity, also called the gravitational field strength. Hey, that's convenient. Okay. Could you get the could you get the G by itself? Times by 2, divide by t squared. You could find G, and then you could plug it in there. Okay. So there is a way of using gravitational field strength and Newton's law of universal gravitation. I'm not going to do the rest of it, but I'm sure it works out quite nicely. Or I could give you the mass of the planet and say find the radius. Or I could do something now. I could actually ask you to calculate G, the gravitational field strength, which it turns out I think is just that. See it? And Fg equals Fg, the little mass cancels. Little g equals big G, big M over R squared. And do something with that in terms of free fall. That would also work. Or in terms of forces. That would also work. Good, 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 good. Coming back to you, I hope. Orbit. Show what? Absolutely. Unless it's talking about energy and work. Is this talking about energy and work? Read it. What am I asking you to find? What else could I ask you to find? Orbital radius. Or what else could I ask you to find? Orbital period. They all started out with Fg equals Fc. And then it depended on what information they gave you. But I totally agree with you, my friend. I'm going to start out by saying, hey, gravity is what's pulling me in a circle. Remember circular force? Your net acceleration was always toward the center. Your velocity was always tangent to the radius. You with me, Nico? Good? Because your genes looked really fascinating to you right then for some strange reason. Don't ask me why. Big G, big M, little m over r squared equals, don't forget the mass, because on your formula sheet, there is no FC equation. There's only an AC equation. You need to clue in force is mass times acceleration. Which acceleration equation am I going to use here? What if it had asked me to find the period? Or had given me the period and said find the radius. Okay, so I can mix and match. Hey, conveniently here, the r cancels. Now, the r doesn't always cancel. If you use the period equation, the r is on the top. You don't cancel an r. In fact, you end up with an r cubed. In fact, there was one situation where we ended up having to cube root sometimes to try and find something. Anyways, and the mass cancels. I guess the orbital speed is going to be the square root of big G, big M over r. Let's see. It's the sun. What's the mass of the sun? Good. You know that it's somewhere on your formula sheet. Excellent. Big G is 6.67. Hey, let's practice typing this in. So this is 6.67 times 10 to the negative 11. What is the mass of the sun? I just know it's big. Orbital radius. Now, did they give me a radius or an altitude? Radius. What if they gave me an altitude? I would have to add the radius of whatever planet we were talking about to get the orbital radius in total, right? Because an altitude was only a height. But here they gave me the orbital radius, 7 times 10 to the 9th. So type that in, press equals, and then square root your answer. Sorry? Can you give it to me in scientific notation, please? 1.37. Is he right? 1.37 times 10 to the what? Is it 37 or 38? 3. Okay, 1.37 times 10 to the 5 meters per second. Okay. This was a part A for 5 marks. I think part B was find the period or something like that. Start out with the same approach. Use the period equation. Be careful when you cross multiply. What else? We also did some involving work and energy. How much work it took to lift up something. How much work it took to put something in orbit. I don't have time to do one like that. Please look at your notes, look at your review, look at your 4 provincial exams that I gave you. Oh. Then we got moved, then we shifted. We moved to electrostatics. We went from physical objects to objects that we could no longer see, that we just had to imagine. So when we talked about charges, we said that there was Coulomb's law, the electric force between charges, but we said what exerts that force on a charge is the electric field. We said that as soon as you put a charge into free space, it sends out an electric field in all directions, like invisible tentacles of an octopus. And it's that electric field that exerts a force on other charges. We said sometimes I'll ask you to find the net electric field from two charges, much like this. How would I do this? Well, are we point charges or parallel plates? So look at your formula sheet. Remember which ones were for point charges, which ones were for parallel plates. If the equation had an R in it, radius, that works for point charges. What do they want me to find in this question? Electric field at point P. How many points are sending out an electric field? I'm going to find them both, magnitude and direction, and then add them vectorially. So I'm going to find them each individually. First one I'm going to find is electric field of charge 1. What is the equation for the electric field from a point charge? So it'll be KQ1 over R squared. It's going to be, K was 9 times 10 to the 9th on your formula sheet. What did micro mean? Yeah, it's on your formula sheet, but it's worth having. 70 times 10 to the negative 6, all over. What am I going to use for my radius here? We're finding the electric field right there. 10 squared. Can you crunch that, please? Usually we get electric fields that are in the thousands or the tens of thousands. So I'm expecting, I hope, an answer, something like that. 6,300? Units. What was the units for electric field? Coulombs is charge. I'll give you a hint. There is an equation that has electric field, charge, and force in it. Get electric field by itself and figure out the units. Newtons per Coulomb. There's another equation that has electric field in it. Find the other equation that has a capital E, not energy, a capital E. Get it by itself. What's the other units for electric field? Volts per meter. Yes? See it? And don't get the EP confused with the capital E. EP, potential energy. Okay. Direction. That's the magnitude, but electric field is a vector. The first row is a vector. We also said for forces and fields, forget the signs. We're not going to put negatives and positives in. We are going to put negatives and positives in for scalars. For scalars, put the signs in. The scalars were the next couple of rows on this. What's the direction? How did we define the direction of an electric field? Which way a positive would want to move if it could. So let's pretend there's a little positive right there. Which way would it want to move because of this guy if it could? Let's find electric field of charge 2. That's going to be KQ2 over R squared. That's going to be 9 times 10 to the 9th. Not negative. And its radius is 4 squared. What do you get? What do you get? 1 point. Is that correct, folks? Direction. Which way would a positive want to move if it could because of that guy, if it was sitting right there? How am I going to add those up? Are they in the same direction or opposite directions? Then go winner minus loser. The bigger minus the smaller. Which is what? Four point. Okay. What else did we do? Well, then we got into the concept of energy and charges. We said that you can think of a point charge as falling or flying away, it was a little trickier than with gravity because charges can repel or attract depending on the energy it has at that location. For example, snooze, you lose. Here was one from my era. It says a proton enters an electric field. I would probably have chosen to underline the word proton because that's going to tell me the charge and the polarity. A little too far. A proton enters an electric field in the direction of the field and is accelerated by a potential difference of 1500 volts. What's another word for potential difference? How do you know? Because look at the units. It leaves the field with a velocity of 7.8 times 10 to the 6th meters per second. What was the original velocity of the proton as it entered the electric field? This is the same as dropping a ball in a gravitational field. It's the same physics as dropping something, only instead of a gravitational field causing it to accelerate, which kind of a field is causing it to accelerate? Now, if I asked you to analyze this, there's a change in height, you would, I think, do it in terms of energy. And that's how we're going to do this as well. We're going to start out saying this is a conservation of energy question. The kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final, Mr. Dueck. No heat. Are any of these zero? Is it starting at rest? What's it asking you to find? The original velocity. Do you think the answer to that would be 0? Is it starting at rest? No. The initial potential energy is coming from the voltage and the electric field that it's traveling through. That's why we said in circuits voltage was like height. That's your PE initial, your potential energy initial. It's not coming to a stop, but you know what? Once it goes through all of the voltage, it's used up all of its potential energy. It's as though it's hit the ground, except instead of hitting the ground, it's just going to keep moving in a straight line at a steady speed. What's kinetic energy? What's it been since physics 11? What? Where'd you get QV from? That's not on your formula sheet. Okay, you have to rearrange an equation. Yes, see it? There is an equation that has potential energy and a charge and a speed. Why? Q, and this is where I said to you, start using big wings on your V so that you can see V for voltage as opposed to V for speed. Equals a half mV final squared. Now what? What are we trying to find? This is, I think what I would do, I don't like the 1/2s. I would probably say times by 2, times by 2, times by 2, because that'll cancel, and I'll get a slightly nicer equation. I'll get mv initial squared equals, Mr. Dueck, plus 2qv equals mv final squared. I would argue that looks cleaner. Now what? Minus 2qv and then divide by m and then square root. So we have mv final squared minus 2q voltage divided by m. Did I miss something? No, I'm good, yes? Is that right? Yeah, I think that's right. The F didn't really cross properly. There we go. They didn't tell me the mass. It's a proton! Okay, so you know it. V final, they gave me. Q, it's a proton. 1.6 times 10 to the negative 19. Big V voltage, potential difference, 1500 volts. Now, you can do this then using QV voltage, or you can also do this for point charges, as well as for, this is for parallel plates, where you know the voltage between the plates. I'm not going to crunch the rest of the numbers. I'm going to assume you could. Another question might be, instead of giving you this between parallel plates, to say something like this. Okay. A proton traveling at 4.8 times 10 to the 5th meters per second approaches a gold nucleus head-on. Okay. The gold too far. The gold nucleus contains 79 protons. I guess a charge of 79 times 1.6 times 10 to negative 19. What's the closest distance this proton can approach the gold nucleus? This is the same physics as dropping an object, except in this case, instead of the object speeding up because it wants to fall, instead, it's going to get repelled. But this is a job for conservation of energy. Can you visualize it? So what we're talking about here, we have a proton, we have a big positively charged gold nucleus. It's starting out some very far distance away. It's moving, it's moving, it's moving, it's moving, but it's getting repelled, it's getting repelled, it's getting repelled. Eventually, it will come to a stop. It will have used up all of its kinetic energy, and it will now want to fall away. Kinetic energy is still a half m v initial squared. Now, potential energy, this is going to be the potential energy between 2 point charges. What's the potential energy between charges? And I think what they're asking me to find is that. Oh, why can I do that? For a split second, when it says what's the closest the proton will get to this gold nucleus, it's going to be slowing down, slowing down. It's going to come to a stop for a split second. Then it's going to start getting repelled, but that we're talking right here. Yes? Oh, what's its initial potential energy? What's its initial radius out at infinity? I think we can say relative to 0 at infinity. We're going to say, you know what? All it has is kinetic energy. We fired it from the edge of the universe. We've given it some kinetic energy. How close will it get before it runs out of steam? You okay with that, Akemi? Because you're not looking good. You gonna make it? Some of you guys are dying. What's my initial radius? Does the question say? Does the question say the initial starting point, the initial radius? What we're assuming then is we're starting relative to 0 at infinity. Okay? You okay with y at 0? And now I could get the R final by itself. Other questions, I could start out with 2 positive charges, one held in place, and I could say when you let it go after 5 meters, how fast will it be traveling? You start out with the same approach. Other stuff would be 0 and canceling, some wouldn't be. Okay. Is that all right? Then we moved on to, do I have more electrostatics? Maybe I do, I can't remember. Because electrostatics is one that kids really find tricky and get mixed up on. Nope. Then we moved on to circuitry. Circuitry, we had, our ski run and Ohm's law, our ski run analogy and Ohm's law and Joule's law bailed us out of 99% of this. Then we just had to remember the concept of terminal voltage and EMF. So here's an example. It hits you back. Circuit. Brett, what do they want you to find? What is the terminal voltage? The terminal voltage is EMF minus the little bump that you lose there. That's all it is. That's what that equation on your formula sheet meant. Oh, the reason it says plus or minus, as we said, that also explains how you trickle recharge a battery by forcing a current backwards up the battery in the opposite direction. That little plus, that little bump, that's what slowly recharges the battery. That's why we can't recharge a battery in 30 seconds. We need some type of different battery technology to do that. So it does say plus or minus on your formula sheet, but I said to you, you know what, recharging, I've done that, it's cool, but I'm not going to really be assessing you on that. So here, what do we say our strategy was for any circuit? Always the first thing you want to try and find is total current. Hey, they gave it to me. If they do not, then your strategy is going to be look for anywhere they told you two things, because if you know two things, you know four things. If you know two things, any two of current, voltage, power, and resistance, you know the other ones, and then often the question fell apart. If that was not available, then you rewrote the circuit as one resistor using your parallel resistor laws. 1 over R parallel equals 1 over plus, and then reciprocal. And your series resistor laws, which was just add them straight up, and then you could go V total equals I total, R total. Here, though, they did tell me total current. Total current is 0.77. That means 0.77 amps is going through there. Okay? Does that mean 0.77 amps is going through here? Yes or no? That's meant to be really easy, folks.
Yes.
No.
No.
What was current? Current was skiers. Zach, some go this way, some go that way. They split up. They split up. They split up. Okay? So, I cannot say, oh, that's going to be that there. This one's a bit tricky because they also didn't give me the internal resistance. If they'd given me the internal resistance, I think what I would probably do then is I could say, I could walk a path and I could find, well, I'm starting with 12 volts. How many do I lose going through? Notice anything about these resistors? One's twice the size of the other. How's that help? There was actually, first of all, if this was 20 ohms, then I would say this split up in half. This would split up into whatever 0.77 divided by 2 is. It would go half there and half there. Or if both of these were 40 ohms, if both the resistors are identical, you can be sure that the current splits in two. They're not identical. Sorry? It's going to split in a 2-to-1 ratio. Now, that's a bit obscure. You know what? Let's write this mathematically as one resistor. They're in parallel. So if I want to write this mathematically as one resistor, I would say 1 over R parallel equals 1 over 20. On your calculators, go. What is that the same as? Sorry? Sorry? 13.333. Anybody else? Yeah? So mathematically, this circuit is the same as this. 12, 13.33 ohms. Mystery, I don't know. Oh, and a current of 0.77 amps. Now let me scroll down so you guys can see. Graydon figured it out again? Pardon me? Oh, showing Coulomb button? That reciprocal button? Pardon me? I don't know. X to the negative 1 or 1 over x? I don't know which one it is on yours. Expecting you to know how your calculator works, right? You good? Ready? This is the mathematical equivalent. It's a little small. That's the mathematical equivalent. With me, Yu-Chen? What's the current right there? Look up. What's the current right there? Yu-Chen. What's the current through the mathematical equivalent then? Now I can say 0.77 amps is flowing through that mathematically equivalent single resistor. What's the voltage through that then? Sorry? You went I times R? You said the voltage, sorry, what was it? Is he right? 7.27 or 10 point? I can't hear, sorry, that's why I'm saying speak up. 10.27? Ready? Look up, look up, look up, look up. How high? How high? What do you lose? 10.27. What's left? Because this is the only other ski hill before I get to the bottom of the chairlift. What must I lose going through here? 1.73 volts. What did they ask you to find? What's the terminal voltage? Maximum theoretical minus the bump. In your head. The terminal voltage is going to be 12 take away 1.73. I can get 9.2. No, sorry, no, you're right, 10.27. Bad math. 10.3. Okay, terminal voltage is 10.3. That's a real quick review of some of the circuitry stuff, and the fact that a bunch of you are thinking that the current was the same in both scares the heck out of me. By the way, what is the same in both will be the voltage drop. If I went back, if they had instead of asking what's the terminal voltage, if they had instead said, hey, what's the current flowing through this resistor here? Now I could do that, because I could say, what did you tell me the voltage drop was through this guy? 1.73. That means this one uses 10.27 volts and this one uses 10.27 volts, because we can shake hands and meet up. We both go through the same height drop. And now I can analyze whatever you want me to. You want me to find the wattage in any of the resistors, the power? I can do that. You want me to find the current in any resistor? I can do that. I can find whatever you want to. But there is a very, very quick review of circuitry. I'm not reviewing magnetism. That's close enough in your memory that I hope it's in your brain. That is in about, 50 minutes, an entire review of the course. I hope that kind of brushed off the cobwebs. I am going to print this up for you in just a second. Let me first of all hit pause. I think I got time to even send this to the photocopier.